how does a ball's horizontal motion affect its fall? The trivial answer to that question is that it doesn't. But a more complete answer is that the ball's horizontal coasting motion has no effect on its vertical falling motion. The ball is doing two things at once. It's falling vertically while it's coasting horizontally. The space we live in is three-dimensional, and so motion occurs in three dimensions. Up until now, I focused only on the vertical dimension, the ball's altitude or its height above the ground. In more general cases, the ball can move horizontally as well as vertically. And if I throw it up at an angle, it does two things at once. It falls vertically, it goes up and down like a falling object, but at the same time, it coasts horizontally at a steady pace. Geometry tells us that in three dimensions, we can describe a ball's position, or any other vector quantity for that matter, in terms of coordinates along three separate directions. Now, we have some flexibility in choosing those directions, but the best choices are three directions that are perpendicular to one another. So, for example, I have this box. Boxes are made in such a shape that if you put sticks along three sides, you have three mutually perpendicular directions pointed out. So here's one direction, a second direction that is at right angles to the first, and a third direction that is also at right angles to both of the previous directions. So this is a system that is three perpendicular and mutually perpendicular directions. And any of these is a pretty good choice of coordinates, of coordinate directions along which to describe any vector quantity you like. When describing the motion of a falling ball, there's one particularly simple choice of coordinate directions. In that choice, one of the coordinate directions points straight up. The second points horizontally along the path that the ball is taking. I call that direction the downfield direction because if you're playing American football or soccer, then you're trying to make progress along that downfield direction. The third coordinate points to one side or the other, and it actually doesn't matter in this situation. So here are the three simplest coordinates. One of them points straight up, one of them points horizontally along the downward direction, and the third points to the side. Well, with that description then, we can look at how a ball falls. If I drop it from rest or toss it straight up, then all of its motion is along that vertical coordinate direction. But if I throw it up and at an angle, it moves both along the vertical coordinate direction and along the downfield direction. Now for something remarkable. A falling ball's motion separates perfectly into two parts, a vertical falling motion and a downfield coasting motion. The ball's vertical motion, that is, the component of its motion that lies along the vertical coordinate direction, is that of a falling ball. And the ball's downfield motion, that is, the component of its motion that lies along the downfield coordinate direction, is that of a coasting ball. And the ball is doing both of these things simultaneously, and they have no effect on one another. To give you an idea of why this works, before I set out and show you that it works, let's look at how the ball accelerates. The ball is being pulled downward by gravity, and so its acceleration is straight down, perfectly along the vertical coordinate direction. The acceleration of the ball is entirely along that vertical coordinate direction, and so the component of the ball's acceleration along that direction is the entire acceleration. Therefore, the ball accelerates along the vertical coordinate direction perfectly. It's a falling ball along that direction. Everything relating to falling is taking place along that coordinate direction. On the other hand, there is no gravitational force component pointing along the downfield direction. That downfield direction is horizontal, and gravity is a vertical effect, so the ball has no acceleration due to gravity along the downfield coordinate direction. Gravity has no effect on motion along the downfield coordinate direction, and so the ball simply does what it was doing in accordance with Newton's first law. It's unaffected, and therefore it coasts. It travels. It's the component of its velocity along the downfield coordinate direction is constant. So the ball's motion vertically is that of a falling object. Its motion along the downfield coordinate direction is that of a coasting object. Well, let me show you this. I need more room, so we're going to go up to the third floor again and throw things out the window. Now, I want to make the ball head horizontally fast so that you can see that downfield motion. And because a bowling ball has a pretty big mass, I can't throw it sideways very fast. That's an inertia issue, right? So I'm going to stick with a basketball. So here we go. I'm going to throw a basketball out the third floor window of the physics building at UVA, and I'm going to get it going horizontally as fast as I can so that you'll see that downfield coasting motion. At the same time, the ball experiences the vertical falling motion. So here we go. So here goes a basketball. I'm going to throw it as horizontally as possible. So it'll start with no vertical component to its velocity. Ready? Get set, go. The basketball's fall and its subsequent bounces took a few seconds, but it's still hard to see what happened in real time. So I'm going to use the fact that this is video to show you that same arcing descent, but with the images of the basketball lingering on the screen. So recall that this camera takes 30 frames per second, so the images that you'll see in a moment are separated in time by 1/30th of a second. So here again is the ball thrown horizontally out the window and arcing downward in the arc of a falling ball. So, that trail of basketball images allows us to determine the basketball's position, velocity, and even acceleration at each moment during its fall. Now, I'm going to concentrate first on the vertical motion of the ball. That is, the component of its motion that lies along the vertical coordinate direction. And I'm going to show you the same video slowed down to 1/10 of normal speed so that you can see what's happening. And I'm going to mark the ball's vertical component of position and vertical component of velocity every 1/5 of a second as it plummets. So here again, same basketball fall, but with slow down and with the vertical components of velocity and position there for you to see. As you can see, the vertical component of the basketball's motion is that of a falling object. There's no difference between the vertical component of motion of this basketball, which I threw sideways to start with, and the bowling ball that I dropped previously from rest out the same window. In both cases, the ball is accelerating downward at the acceleration of gravity. Its vertical component of velocity is increasing in the downward direction by about 10 meters per second every second. and the ball is covering more and more distance with the passing time. So the vertical motion of a falling ball is that of falling, regardless of what its horizontal motion is. So now I'm going to show you the same video again at 1/10 normal speed, but instead of worrying about the vertical component of motion, I'm going to worry about the downfield component of motion. That is, the portion of the motion that's occurring along the downfield coordinate direction, which will be toward your left. So here's the same video in slow motion with the horizontal component of position marked off every 1/5 of a second. As you can see, the downfield component of the ball's motion is that of a coasting object. The ball moves steadily downfield, equal distances and equal times. So the downfield component of motion is that of an inertial object. The ball is experiencing no force along that downfield coordinate direction, and so it's not accelerating along that downfield coordinate direction. It's simply coasting horizontally. So the ball is doing two things at once. It's falling vertically, it's coasting horizontally, and that gives you the arc that you saw as the ball descended out this window, starting horizontally and then arcing downward until finally it hit the ground. Well, that was a basketball falling out the window. The story will be identical if I throw a bowling ball out the window. And of course, it's fun to throw bowling balls out the window. So you wanted to see it, I'm sure. Here we go. Ready? Here goes the bowling ball. Didn't bounce much. Well, that was fun. I think I better go repair the dent. Now, bowling doesn't have much to do with falling balls, but basketball does. Still, tossing basketballs out the window isn't how the sport is played. Instead, it's played on a court by people throwing the ball either between themselves or toward the basket. And once the ball is free from anybody's hands, it's a falling ball. So basketball is all about falling balls. To see that, let's go over to the gym and watch some people shooting hoops. Once the basketball leaves the hands of the shooter, it's experiencing only one force, its weight straight down. And so it's a falling ball, and the arc that it travels in is the arc of a falling object. Every time a player takes his shot and the ball leaves his hands, the ball begins to fall, and it travels in the arc of a falling object. I could take any one of these shots, show you the trail of basketball images, and then show you that that trail is the arc of a falling object. Here are a couple of those curves. I will show you the arc that's formed by the basketball images, and then I'll show you both the vertical motion and the horizontal motion. So you can see that the vertical motion is that of falling and the horizontal motion is that of coasting. Now, depending on the perspective we have on a particular shot, some of the distances get compressed as the ball gets farther away from us. And so the evenness of the horizontal motion may be not perfectly visible. Nonetheless, this basic behavior of falling vertically and coasting horizontally is everywhere in the game of basketball. Here is a beautiful three-point shot right through the basket. And here is that same shot again with all the previous basketball images lingering on the screen. And here is a still photograph of that same shot showing you all the basketball images, and I've marked it up so that you can see the ball's vertical component of motion and its downfield component of motion. The ball's vertical motion is that of a falling object. The ball rises quickly at first, then more and more slowly. It's momentarily neither rising nor descending, and then it descends more and more quickly as it approaches the basket. The ball's horizontal motion, the motion along the downfield coordinate direction, is that of a coasting object. The ball is moving steadily downfield at a uniform pace, and it looks like the vertical yellow lines are getting closer and closer together only because the ball is getting farther and farther from us. And because of our perspective on this shot then, the lines that are far away from us appear closer together because the space out there is compressed. It's just off in the distance. So this really is the arc of a falling ball thrown up at an angle, and basketball has lots of these arcs. Every single shot is like this. Here's another nice shot through the basket. And here is that same shot with a trail of basketball images lingering on the screen. Lastly, here is a still photograph of the same shot marked up to show you that the basketball is falling vertically and coasting horizontally. It's time for a question. I have an orange ball and a black ball, and I'm going to roll them off the table side by side and let them hit the floor. The black ball weighs twice as much as the orange ball, but the orange ball will be moving to your right twice as fast when the two of them leave the table. The question is, which ball will hit the ground first, and which ball will hit the ground farthest from the table? Here we go. Ready, get set, go. Both balls left the table with the same vertical component of velocity, namely 0. In effect, they began their fall from rest. They dropped together and hit the floor at the same time. But the orange ball was traveling sideways faster. It had a greater downfield component of velocity than the black ball, and so it used its time to travel farther from the table and hit the ground farther from the table. The arcs of falling balls are part of nearly every ball sport, including football, basketball, baseball, and soccer. Effects due to the air modify those arcs somewhat, and we'll deal with those air issues in later episodes. But even if we continue to ignore air, we can make some interesting observations about how ball sports work. Whenever you throw or kick or hit a ball, there's usually a limit to how fast you can make that ball move. For example, I can only throw a baseball so fast. Let's suppose that you throw a ball as fast as you can. What path does that ball take? Well, that depends on the direction in which you throw it. I've set that upper speed for the ball, but I haven't selected yet its velocity. Remember, velocity is a vector quantity and has a direction to it. So when you throw the ball, you're choosing not only its speed, and we'll choose the maximum, but you're choosing the direction of that ball's velocity when it leaves your hand. Well, when you choose the ball's velocity, in particular the direction of its velocity, you're choosing both the vertical component of the ball's velocity and its downfield component of velocity. If you throw the ball straight up, you're putting all of that speed into the vertical motion and giving the ball its maximum vertical component of velocity. At the same time, though, you're giving the ball 0 downfield component of velocity. So straight up, it distributes all of the speed in the vertical direction. On the other hand, you can throw it straight horizontally and give the ball put all of the ball's speed into the downfield component of velocity, none into the vertical, and everything in between. Well, that choice of angle, and we'll measure angle relative to horizontal. So this is 0 degrees on up to 90 degrees. That choice of angle at which to throw the ball has a big effect on the ball's path. It determines both how long the ball stays above the ground and how far it travels downfield during its time aloft. Let's start by throwing the ball straight up, that is, 90 degrees above the horizontal. Here is a plot of the ball's position, both its vertical component of position and its downfield component of position at equal times during its travels. By throwing the ball straight up, you're putting all of the ball's initial speed into its vertical component of velocity and none into the downfield component of velocity. That ball has the maximum vertical upward speed, and so it rises to the greatest height it can go to and takes as long as possible to return to the ground. But of course, it makes no progress downfield at all because you haven't given it any downfield component of velocity. It hits you on the head, which isn't typically very useful in most ball sports. Let's try something else. Let's lower the angle at which we throw the ball to about 70 degrees. In this case, we're putting the ball's speed mostly into its vertical component of velocity, but still somewhat into its downfield component of velocity. At this point then, the ball doesn't stay above the ground as long. It simply doesn't have as much upward component of velocity. But it uses the time it's above the ground to make progress downfield, and it lands somewhat downfield. This is good. You didn't get hit in the head again. All right, let's go to a lower angle. Let's go down to 45 degrees. 45 degrees is special because at that angle, you're distributing the ball's initial velocity equally so that the vertical component of velocity and the downfield component of velocity are the same. They're in different directions, but they're equal in amount. And so the ball has a perfect balance between the vertical motion, which keeps it above the ground, and the downfield motion, which causes it to travel in the direction you want it to go. And with this perfect balance at 45 degrees, and in the absence of air changes this somewhat, the ball stays aloft long enough and travels downfield fast enough to travel as far as you can make it go from where you threw it. So if you throw it from this height, it will pass through this height again as far as possible downfield. All right, let's lower the angle still further from 45 down to about 20 degrees. At this point, you're putting most of the ball's initial velocity along the downfield direction so that the downfield component of velocity is quite large. There isn't all that much vertical component of velocity left. The ball doesn't stay above the ground very long, but it uses what little time it has to travel very fast downfield. Finally, if we go all the way down to horizontal, the ball in principle doesn't stay above the ground at all. I mean, it depends on, in fact, you throw the ball from up here and the ground's down there, but if you threw the ball from ground level horizontally, it would hit the ground immediately. So a totally level throw is often not very valuable if you're low. But for baseball, for example, it's not bad because you are far enough above the ground that the ball can stay above the ground by the time it gets to home plate. All of these possible paths are potentially useful in ball sports. For example, if you're going for maximum distance with a football, you probably want to throw it about 45 degrees above the horizontal because that gives you the best balance between vertical component of velocity and downfield component of velocity to maximize its flight distance downfield. But sometimes maximizing that distance isn't your goal. For example, a punter kicking the ball to the other side may want to keep the ball out of the hands of the opponents as long as possible while still achieving some amount of downfield distance. And so a punter will often kick the ball above 45 degrees, more like 70 or 80 degrees, so the ball has a longer time above the ground, even if that costs some amount of downfield distance. On the other hand, if there are players all over the field in football and you want to throw the ball to someone as quickly as possible, and they're not all that far from you, distance isn't the goal, it's speed downfield, in which case you want to throw the ball below 45 degrees, more like 20 degrees or maybe even 10 degrees, to put as much of the speed in the downfield component of velocity as possible, to get it there fast. So, in all the sports, choosing those angles matters. It gives different flights, and many of them are useful.